Good afternoon, man. I'm Xiaochen Jiang from Computational Marine Hydrodynamics Labs, Shanghai Jiao Tong University. Today, my talk is numeral simulations of partially filled spherical tank sloshing using Openfoam in comparison with experimental results. I will give my speech in 4 aspects. Firstly, the background of sloshing and motivation. Then the method and the model of simulation will be introduced. After that, a series of simulation results will be discussed and the conclusions were drawn. First, liquid sloshing is the phenomenon that occurred in our daily life when a liquid within a container moves or shakes. It is also a classical multi-phase dynamic problem and occurs in various engineering such as aerospace and marine engineering. This sloshing not only affects the stability sorry. The mouse I can okay. And the safety of the carrier, but it can also induce structural resonance, raising the integrity of overall structure, such as vibrations during launch, impacts from waves, or maneuvering operations. The fluid inside the tank exhibits complex sloshing motions, so it's of great importance to study this phenomenon to reduce the liquid sloshing. An increasing number of researchers have studied these hydrodynamic problems. From the figure, we could see that in the past 6 years, papers on sloshing were cited an average of 7,000 times per year, and in 2022, the number of citations reached more than 10,000 times. In recent years, different scholars have used many methods to explore the mechanism behind the sloshing and try to analyze the roots. In the 1960s, Sumner obtained a simplified theoretical model through experimental summary to further analyze its mechanism. Scholar soon proposed an equivalent model to predict the response of the elliptical cylinder storage tanks. With the development of computation technology, a large number of numeral simulation methods began to appear, in which young scholars use MPS method, particle method to focus on the Faraday waves generated in the process of sloshing to study the vertically moving rectangular tank. Given that sloshing force can impact the stability of ships, offshore structures, and aerospace vehicles, researching how these forces are generated or composed is indeed invaluable. So there is a question, how do different excitation frequencies affect the sloshing of the tanks? Although there are many numerous studies on the hydrodynamic behavior of fluids inside tanks, most research focuses on traditional cylinder or rectangular tanks. For spherical tanks, due to their unique geometric structures, the dynamics of the internal fluids exhibit distinctive complexities and challenges. Moreover, existing studies largely concentrate on sloshing modes under low-frequency excitation, while excitation under high frequencies are rarely explored in depth. Against this backdrop, this study aims to fill this gap by using Openfoam multiphase solver to investigate the dynamic response of fluids in spherical tanks under various excitation conditions, particularly revealing the novel rotational sloshing phenomena under high-frequency excitations. Now let me introduce the combination method. In our work, safety techniques with the Euler method is taken into account. The built-in solver Interform offers detailed visualizations and precise control over boundary conditions and perform well at free surface flow and captures fluids nonlinear dynamics. The Gaussian equation is the continuity equation and the Navier-Stokes equations. To U is the velocity, PD represents the dynamic pressures, mu is the kinetic velocity, G is gravity, and the acceleration vector. T and F sigma indicates the time and the surface tension force respectively. The free surface capturing is an artificially compressed volume VOF method. The advantage of this method is that it can control numerical precipitation and has high accuracy in capturing free surface. The VOF also solve a transport equation in terms of volume fraction of fluids. This slide shows the computational methods of free damping parameter extraction and the dynamic grade method. The initial free surface will be set 5 degree inclined for horizontal, and the center of gravity of fluid is captured in the process of free decay simulation. By extracting the extreme value and referring to the literature, we can calculate the natural frequency and the free decay coefficients at the corresponding liquid filling rates. By setting the boundary condition to moving velocity, the cylinder excitation is exerted. The animation is shown above. Okay. Discrete schemes for different terms in equation was shown briefly in this table. We won't go into much detail here. The coupled pressure and velocity term is solved by pimple algorithm, which is a merge pistol pimple method. Now let me show the computational method and the verification. Here is a sketch showing basic parameters of simulation. The h is the height of free surface from the bottom of the spherical tank. The excitation is at the direction of x-axis and x0, and omega e is the excitation amplitude and the circular frequency respectively. To begin with, a mesh convergence is carried out with 3 different total mesh numbers: 2,060,000, 380,000, and 520,000 under this condition. We can see from the Sloshing force time history that these 3 curves fit well, and there is basically no difference. The slight difference in the curve shows in the peak of the value is the red and the blue lines are always closer. Second, according to the maximum force in table, the error is less than 3% only, and the result of medium grade is similar to that of fine grade. So we choose the medium mesh to the further study. Besides the free damping simulations above of the conditions that have come down to analyze the sloshing force and the flow field, the main difference is the parameters of non-dimensional excitation frequency. Now, this part we will show the results and discussions. In the beginning, we simulated free damping at this filling rate H to R ratio equals 1.2. The gravity was captured, and we obtained that the natural frequency is 8.4. The damping ratio is 0.00275 respectively. It is worth noting that our work rectifies the free damping ratio error by simulation of cylinder tank sloshing, and is less than 1% from other researchers' results, which means the free damping simulation is accurate and reliable. We firstly show the simulation results under the frequency ratio of 0.6 and 0.4, and the left side shows the time history of force, and the right side shows the flow field. It is shown that both simulations of liquid motion are basically in x-axis. We can see that when the frequency ratio is 0.4, as shown by the left one, the lower frequency shows a mole component of free decay natural frequencies. The maximum is 10.58 and 24.45 newtons respectively. Now we add the condition of excitation frequency omega e equals 0.8 natural frequency. Omega 0 time history of sloshing force shows the obvious increase, and the right side shows the flow field of numerical simulation and experimental results at the same condition. From observing the animation, we conclude that the movement of the fluid is still basically in the x directions, while there's some slight fluctuation on y directions, and the changes is linearly. The simulation of flow field shows a good agreement with experimental results in linear change. The maximum is about 55.2 newtons, more than twice the value of previous condition. Next, the condition shows excitation frequency equals to the natural frequency. We could see that there is a significant change in flow both field and oh, there's a little clinch. The free surface was excited to a long linear changes with a rotation wave. It is worth noting that when there is no resonance excited, the liquid does not rotate with an agreement with experiments. This phenomenon shows the importance of the experimental verifications, and the maximum is about 84.79 newtons. For the black line, we can see that there is an envelope line in the extreme value, and a some force component excited to y direction. This two wavelength phenomenon is not totally the same. As we continue to increase the excitation frequency to 1.2 times natural frequencies, the flow field with agreement with two results also shows a high order free surface changes, like S-shaped wave in the surface and some jet wave. It is found that the sloshing force value extreme largely decreases. With a sudden change of force, the maximum is around 22.66 and 31.93 in opposite x directions, nearly 3/8 less than the resonance condition, and similar with the condition with omega e to omega 0 equals 0.6. We can see that the sloshing force is decreased in a large scale. At last, we carry out the fast Fourier transformations of the time history of sloshing force and obtain the above figure. The maximum value is listed on the right side, and it is shown that the maximum of force spectral density is nearly increasing linearly with a drop at the highest excitation frequency condition. Now we do, in summary, a series of numerical simulations of partially spherical cant with parameters, different parameters omega e to omega 0 were conducted, and the following conclusions are drawn. Firstly, the simulation results are in good agreement with the experimental results. The Openfoam multi-phase solver interform could accurately simulate the sloshing phenomena, including the free damping and the free surface change while sloshing. When the excitation frequency equals to natural frequencies, the resonance occurs and force sloshes with an envelope line in condition omega e to omega 0 equals 0.8 can also observe the envelope line history, but the rotation in flow field is found simultaneously, so the mechanism is not the same. At higher excitation frequency, the wave force will be greatly dissipated in the flow field so that the sloshing force will be significantly reduced. That's all. Thank you.
Okay, thank you for your presentation. Okay, I have a small question. If we wanted to capture the matter phase of the flow, then flow dynamics or the free surface deformation when the spherical tank oscillates. So, what are the key physical models or numerical methods during the simulation?
We said we do have the liminal assumption or the k omega, the radial schemes, but in our work we choose to use the linear schemes since we have the conversion and the house and the dissipation of the radial method shows a more dissipation. So, and compared to the experiments, the linear mode can show a good agreement with the reality.
We use another assumption, because you mentioned that you used the linear assumption. Because if we use another assumption, can you guess what will happen?
The dissipation maybe it can be the damping ratio is not accurate as the same in use the laminar mode. It can be a more bigger one.